Welcome to the deep dive. Today, we're tackling a really fundamental question that's buzzing around in AI circles.
hmm
How does reinforcement learning RL actually change the reasoning abilities of these big language models?
Yeah, it's a big one. We're digging into a paper from NVIDIA researchers called ProRL. Prolonged reinforcement learning expands reasoning boundaries in large language models.
So, ProRL. The backdrop here is that, well, modern LLMs are showing some pretty amazing reasoning skills, right? Often using things like chain of thought or extra computation time when you ask them a question.
Right, and RL is a big part of tuning these models, aligning them with, objective rewards, getting the right answer.
But the debate, the real core of it is, does this RL tuning actually teach the model new ways to think? Does it expand its horizons?
Or does it just make the model better at digging out solutions that were kind of already hidden somewhere in its original training data, amplifying versus expanding?
And so earlier research maybe leaned towards the amplifying side, suggested RL wasn't necessarily adding brand new skills based on how they measured it.
Correct. But this pro-RL paper suggests, well, maybe those earlier studies had some limitations in their approach.
Like what?
Specifically, maybe they didn't train the RL part for long enough, maybe just a few hundred steps.
hmm
And perhaps they focused too much on areas like math, where the models were already heavily trained.
Ah, okay. So the hypothesis is kind of like, what if you let the RL run for way longer
Yeah.
and threw a much wider variety of problems
What
at
would
it?
happen then?
Yeah.
Yeah. And that's what led them to develop this new method they call prolonged reinforcement learning, or pro-RL.
Pro-RL. The name says it prolonged. The idea is to really extend that RL training phase, get past those shorter runs people did before.
Make it stable enough to run for much longer.
Okay, but longer RL training can be tricky, right? Models can sometimes go off the rails or performance can collapse. How does ProRL handle that? What's the secret sauce?
A really important ingredient is using a KL divergence penalty. So this basically measures how much the model's current way of generating answers differs from a reference version of itself. It acts like a kind of tether.
A tether, how so?
It helps keep the model from changing too drastically too quickly. It encourages it to maintain some diversity in its potential answers, rather than just collapsing onto one single strategy very early on. Prevents entropy collapse, as they call it.
So it keeps exploring options a bit more instead of just locking onto the first good thing it finds? Makes sense if you want it to potentially discover something new.
It does. And another key part is that they periodically reset this reference policy and also the optimizer states during the training.
Reset them. Why?
This basically allows the model to kind of refresh its learning process. It prevents it from getting stuck in a rut or converging too early, allowing it to continue improving over these really long training periods, thousands of steps.
Got it. So KL, penalty for diversity, resets for sustained learning. What else defines ProRL?
The diversity of the training problems, this seems critical. They didn't just use math problems or just coding.
Right, you mentioned that earlier.
They used a massive set, 136,000 problems covering math, code generation, STEM questions, logical puzzles, even just following instructions.
Yeah, it's a huge range.
And the thinking is that this breadth is really needed for the model to learn strategies that generalize, that work across different types of reasoning, and maybe stumble upon new ways of connecting ideas.
Okay, makes sense. Any other specific techniques involved?
Yeah, they also borrow and adapt some useful tricks from other methods, like DDO, things like decoupled clipping.
Decoupled clipping.
It gives the model a bit more leeway to explore answers that might seem less likely initially but could turn out to be correct, encourages more exploration, and also dynamic sampling.
Dynamic sampling, filtering the problems.
Sort of. It helps focus the training by dynamically filtering out prompts that are currently too easy or way too hard for the model. Keeps the learning signal strong and efficient over that long haul.
Okay, so that's the ProRL recipe. What model do they actually apply this to?
They trained a model they call Nemotron Research Reasoning Quen 1.5b. The key part there is the 1.5b. It's a 1.5 billion parameter model.
Which is, not small, but definitely smaller than some of the giants out there. The 7B models are much larger ones.
Correct. Relatively modest in scale compared to many state-of-the-art reasoning models.
And how long did they train this model using ProRL?
Over 2,000 steps, so significantly longer than those few hundred steps mentioned as a possible limit in prior work. They used the whole ProRL toolkit on that big, diverse 136K dataset.
All right, the moment of truth. After all that prolonged, diverse training, what happened? Did it work?
The results seem pretty compelling. They saw really substantial improvements in performance measured by pass at 1, getting the right answer on the first try.
Compared to the original base model it started from.
Yes, compared to the DeepSeek R1 Distill Quinn 1.5D base model, the gains were across the board, like plus 15.7% on math problems,
Okay, decent.
plus 14.4% on coding tasks. But then look at this, plus 54.8% on logic puzzles.
Whoa, over 50% jump on logic. That's huge.
Huge jump. Also, plus 25.9% on STEM questions, and plus 22.0% on instruction following tasks. Really significant gains pretty much everywhere.
That logic puzzle result is pretty stunning. What else stood out?
What's also really interesting is that this 1.5V parameter ProRL model actually started matching or even beating a much larger model, the DeepSeek R17B, in several areas.
So the smaller model, trained with ProRL, punched above its weight, so to speak.
It suggests the prolonged diverse RL training is really powerful, not just throwing more parameters at the problem. And it even outperforms some models that were specifically fine-tuned just for one domain, like math or code.
Shows the strength of a generalist approach, maybe.
Potentially, yeah. The ProRL training seemed to build broad capabilities.
And crucially, did the improvements keep coming the longer they trained? Did it validate the prolonged aspect?
Yes, that's a key piece of evidence. They tracked performance during training using pass at 1 and also pass at 16, giving the model 16 tries. Both metrics consistently went up as training progressed, even past 2,000 steps.
No plateauing.
It kept scaling with more training compute. This really backs up their core idea that longer RL training, done right, is beneficial.
Okay, so ProRL makes the model better, performance scales with training time. But this brings us back to the big question, right? Is it just making the model sharper at using what it already kind of knew, or is it genuinely discovering new reasoning pathways?
Exactly, and they did dive deeper into the analysis to try and tease that apart.
What did they find?
One interesting pattern was where ProRL seemed to help the most. It tended to expand the model's reasoning boundary most significantly on tasks where the original base model was, well, pretty bad.
Where it struggled initially.
Right. If the base model was already doing okay on a task, the gains from ProRL were smaller. Sometimes, interestingly, the breadth of exploration might even shrink a bit on those tasks, even if the accuracy of the best answer went up.
So it helps most when the model is kind of lost or uncertain to begin with.
That seems to be the trend. They used a metric called the creativity index.
Creativity index, what's that measuring?
It's designed to estimate how much the solutions the model generates overlap with patterns likely seen during its initial pre-training. Lower creativity means more overlap.
Okay.
And they found that tasks with smaller gains from ProRL tended to have lower creativity index scores, higher overlap with pre-training. It supports the idea that RL is most impactful when pushing the model into less familiar territory.
That makes intuitive sense. They also looked at different patterns of improvement across tasks using those pass at K metrics, right? How performance changes with more attempts.
Yes, they identified about 3 different regimes or patterns. The first they called diminish.
Diminish sounds negative.
Well, not necessarily for the best answer. In this regime, pass at 1 improves the model, gets better at finding the most likely solution. But pass at K for higher K, like pass at 128, might actually decrease slightly.
Meaning it explores fewer alternative solutions, gets more focused.
Something like that. It sharpens its aim on the best path, potentially at the expense of broader exploration. They saw this on some math tasks.
Okay, diminish. What's next?
Plateau. Here, the gains happen relatively early in the ProRL training, but then performance just levels off. It doesn't keep improving much with more training. They saw this on certain benchmark tasks, like GPQA Diamond.
So it learns what it can quickly, then hits a ceiling for that task.
Seems like it. But the third regime is perhaps the most interesting for the core question. They call it sustained.
Sustained improvement.
Correct. In this regime, the reasoning capability, measured by pass at K, keeps improving throughout the prolonged training. They saw this clearly in areas like coding and some of the logic puzzles.
And that pattern suggests ProRL really is pushing the boundary, finding better or maybe new ways over time.
That's the interpretation, yes. Sustained improvement points towards an expansion of capability, not just optimizing existing skills.
To really nail this down, though, they needed to test it on things the model definitely hadn't seen, right? Out-of-distribution tasks or harder versions of training tasks.
And this is where the evidence for genuine expansion gets really strong, I think. They highlight a task called BoxNet.
BoxNet! Never heard of it.
It was completely new, totally unseen during any ProRL training. And the base model, it was Completely incapable. Zero success.
Not just bad, but literally zero correct answer.
Zero. Couldn't solve it.
Yeah.
But the ProRL model, after training, it developed a significant ability to solve BlocksNet. The pass at one score climbed steadily with training, and eventually pass at 128 got close to 100%.
Wow. Learning to solve something from scratch that it was utterly failing at before, that feels like more than just amplification.
It's a very strong indicator of generalization and boundary expansion, yes.
Yeah.
And importantly, the extended ProRL training kept pushing these gains higher on this novel task.
Any other examples like that?
Another compelling one is a task called graph color. They trained it on graphs up to a certain size, say 10 nodes.
Okay.
Then they tested on larger, more complex graphs, 11 nodes, 12 nodes, and so on, which it hadn't explicitly seen in training for those sizes.
So testing its ability to handle increased complexity.
Right. And the ProRL model maintained much higher accuracy on these larger, harder graphs compared to the base model or models trained for shorter durations. It showed better robustness and generalization to complexity beyond its direct training data.
And one more piece. They looked at how the distribution of correct answers changed.
Yes, looking at the pass of one scores across all the problems in a task. Figure 7 of the paper shows this well. What they saw was that prolonged ProRL training caused these distributions to shift dramatically to the right for many tasks. Meaning problems that the base model had almost zero chance of solving correctly, pass at 1 near 0, now had a high probability of being solved correctly by the ProRL model. It wasn't just improving scores on problems it could already somewhat handle, it was fundamentally shifting problems from the impossible bin to the solvable bin.
Okay, so let's try to wrap this up. Taking all that evidence, the scaling with long training, the big gains where the base model struggled, the success on totally unseen tasks like BoxNet, handling harder graph color problems, and shifting those probability distributions. What's the main conclusion here?
The central takeaway seems pretty clear from this work. It provides strong evidence challenging some earlier views. It shows that reinforcement learning, if applied for long enough, using the right techniques for stability and diversity like ProRL, it can genuinely expand the reasoning abilities of these models. It's not just amplifying latent skills. It seems capable of unlocking new strategies and pushing the boundaries of what the model can figure out.
And it's particularly noteworthy that they demonstrated this with a 1.5 billion parameter model, right?
Right.
Making advanced reasoning potentially more accessible, not just restricted to the absolute largest models.
That's a key point. It highlights that sophisticated training methodologies like ProRL can be incredibly impactful alongside just scaling up model size.
So it leaves us with the thought then. If this kind of prolonged guided RL can teach a model reasoning strategies it simply didn't have access to before letting it solve problems it was completely failing on. Well, it makes you wonder, doesn't it? What other kinds of AI capabilities, what new forms of reasoning or problem solving might still be waiting out there, ready to be uncovered if we continue to explore these long horizon reinforcement learning approaches?